Good afternoon, everyone. This is lecture 26 of PTRE 475575. I'm recording from the office today because there was an issue with the file upload on Blackboard upstairs. For some reason, I couldn't download them. I couldn't even see the slides for the fifth module upstairs, so I came downstairs to record from here. I think I'm sharing the right screen and I am recording. So last time we finished module 4, which was a pretty nice one, wrap up after we learned a lot about hydraulic fracturing. We talked about how does hydraulic fracturing affects your reservoir wellbore system. And we said it affects the reservoir side, it affects the IPR curve. But we also talked about VLP, the vertical lift performance side. We talked about formation damage and so on and so forth. And you had a pretty elaborate homework on that. Not necessarily a hard homework, but an elaborate homework on that was due last night. You must have made a lot of plots, and then we basically wrapped up module 4 last time. Now I want to show you a slide from the 4th module before I introduce module 5. Let me see, I think it's here. Come on. Temporarily, I'm opening this. There is one slide I want you guys to see, and that is this one. We said in this case, VLP and IPR do not touch anywhere. So the well and the reservoir in itself, with a certain well in place, the tubulars in place inside the well, is not able to bring oil to the surface. So in this case, you need to supply some energy from externally, from outside. So that's when artificial lift is needed to provide the gap. And of course, as time goes by, depletion makes IPR move downwards and to the left. If VLP stays the same, you will need more stronger and stronger artificial lift system that is able to supply more energy to the fluid. So this is where we sort of ended. And now we are really going to focus on artificial lift and surface facilities. It's mostly going to be artificial lift stuff in this module. Reason being also we're going to miss lecture on Tuesday because I'm going to be in Houston for Offshore Technology Conference. So really is this lecture, and if I'm able to record one, I need at least one lecture for the revision before the final. And I really want to dedicate the next lecture on Thursday the 7th to that. I'm coming back on the 6th, and on the 7th is our last lecture. I might record another one if I need to finish this module, but this module is not crazy. Let's put it this way. It's yes, it's 35 slides, but it's fairly easy moving slides. Ideally, I would like to spend like 2 lectures on it, but I can push it with one long one or maybe 1.5 if I record something. So we know what artificial lift systems do or intend to do, but we don't know how they work. And we're going to see briefly, I think, 4 main popular ones. And then there is much more than that. Now, what is artificial lift? Artificial lift refers to human-controlled means of increasing a well's productivity boosting its flow rate while lowering the flowing bottom hole pressure. Now, artificial lift is generally a production subtopic, but petroleum engineering schools, they generally have an elective course. They offer an elective course on artificial lift, and they cover it briefly in production. So because we don't have elective courses in this school, I decided to add a little bit of artificial lift into my class because well completions are related to artificial lift. A big part of well completion is dedicated to that. So I would like you to know what is it used for, etc., etc. Well productivity depends on the use of compressional energy supplied by the reservoir, which declines with depletion. So remember the IPR curve moves to the left and down. So productivity goes down. Less energy can be supplied by the reservoir. Regardless of the selected artificial lift method, adjustments are necessary for the output to continue matching the input available from the reservoir throughout depletion. And what does that mean graphically speaking? There needs to always be an intersection between the IPR and VLP all the time. So you'll be making adjustments even if you are using the same system. Just like I said, over time, you're going to need a stronger and stronger system, but you're also going to be making adjustments within that very system, adjustments in regards to rate, etc., etc. From the excellent book of Bomer and Podio, the Beam Lift Handbook, there is two axioms, the goals, axioms they call them, of artificial lift. You want to produce all the liquid that the reservoir can flow into the bottom of the well on a continuous basis, as long as no harm is done to the reservoir or the well equipment in place. And second, while achieving the first goal of producing at the optimum rate, it is desirable to pump as low as possible, using the lowest speed in order to maximize the lifetime of the well equipment. And I want to stress this second point because you don't hear that a lot outside. You go to a conference, they show you artificial lift hardware, and they tell you about having the maximum possible rate. They are going to talk about maximizing the flow rate. And this is not the only thing that you should care about in the well. In fact, there is many problems, and we are going to see one later today, maybe, that one scenario where slowing the pump actually solves a problem. The design of the equipment must be within the working limits of all components, and the system must be monitored to detect performance changes that might require modifications such that the first three goals are met over the well's entire life cycle. So these are the four axioms of what artificial lift systems are helping us achieve. Now we have brown fields and green fields. What's the difference between the two? A brownfield is an oil field whose production has matured to a plateau or progressed to a declining stage. Improved oil recovery methods, including artificial lift, are implemented to maintain production from brownfields, prolonging their life cycles and maximizing oil recovery. Brownfields is where you will see artificial lift methods being employed to add energy to the fluids inside the well, aiding their movement to the surface. So just like hydraulic fracturing is helping fluids from the rock get into the well, artificial lift is helping fluids from the bottom of the well make it to the surface. I have here a magazine article I wrote in 2022 on artificial lift. Doesn't let me. But you will see a lot of the stuff that we have in this slide deck as well in this article. Now, greenfield is a newly discovered field, not a lot of wells there, not a lot of pressure depletion. So the pressure of the reservoir is pretty high, and we think that it was pressurized well at the beginning. It was discovered at a very high pressure that is enough to sustain fluid flow to the surface. Suction rod lift is the most common type of artificial lift. Now, its official name is suction rod lift. Some people call it beam lift. Most of the people call it the pump jack method. The thing is that the pump jack method name is not smart. It is not a correct one because you can achieve beam lift without a pump jack with a different kind of surface equipment, and and you may not even have a beam. So why do you call it beam lift? Beam is the thing that moves up and down. That part that moves up and down is called the walking beam. So hence the name beam lift. But beam lift is not a very good name. And same thing as pump jack. Suction rod lift is the perfect name because no matter what you have on the surface, if you use this method, you have suction rods. So, and there is a lot of technology going into those suction rods. Also known as beam lift, suction rod lift is the most classic artificial lift method employed in thousands of wells globally. Especially popular in stripper wells of minimal production below 10 barrels a day and below 60 MCF per day, suction rod lift is usually the first choice for most onshore and even several offshore wells. A downhole positive displacement pump is driven by a surface unit with the flagship beam lift pump, beam pump, which is basically what they call the pump jack colloquially, being the most widely used installation. Um, Imagine the downhole displacement pump is like a bicycle pump, okay? You move the bicycle pump and then you pump air out of it, basically. Same way the positive displacement pump is operated by moving a piston up and not a piston, by moving a valve up and down, a certain equipment up and down, and as a result, it makes fluid come up to the surface. A significant advantage of suction rod lift is that it can operate at very low FBHPs, yet its configuration contains multiple moving parts, which implies numerous reasons for maintenance. So if you have a car that has like 30,000 moving different parts, you have 30,000 reasons, possible reasons for maintenance. Each of those parts can break. Similar to the beam lift, beam lift system, the artificial lift system, it has a lot of moving parts, so it's easier to break. That's another reason why we should be running it as slow as possible. We want to prolong the life cycle of these parts. If we need to replace a part on the surface, it's not that big of a deal. But if we want to replace something downhole, we need to bring a workover rig. We need to retrieve the downhole pump, find what is wrong with it, and fix it. It is not an easy process. The workover rig, we call it the gorilla in the room. If the fixing involves bringing a workover rig on site, automatically is the critical point between the bill that you have to pay being huge or something very small. There is no in between. Like once you need the workover rig there, you are in a tough situation. This is how it looks, and this is my own schematic actually. We have a lot of moving parts. The most important is the one that I put my mouse on, walking beam that moves up and down. You have the horse head. That's why many people call it the nodding donkey. And the walking beam oscillates up and down on two Samsung posts, as they are called. And the up and down motion is facilitated by counterweights cranked on a gearbox that are rotating. So the rotation is translated to up and down motion of the beam lift using the crank and counterweights. Now the gearbox basically slows down a motion that already was transmitted to it by the prime mover, which is basically a motor, an electric motor, and so on. Up and down motion on the horse head, makes the polished rod move up and down itself. When the polished rod moves up and down, it basically moves the cycle rods up and down itself. And when they are moving up and down, the downhole pump consists of two valves, as we see here at the bottom left. Two valves that operate with a ball sealer. The traveling valve moves up and down with the horse head. And there is a small ball sealer inside. And then there is the standing valve, which doesn't move, and there is a much bigger ball sealer in it. We see it as green in this schematic. When you are moving up, the traveling valve is closed, the standing valve is open, the ball moves away from the valve, so it's creating a little area from which fluid can get inside that little barrel that is created downhole as you are moving up. So as you are moving up during upstroke, you are filling the barrel with fluid. And then as you are moving downstroke, the opposite happens. Traveling valve is open, the red ball moves away from the gap that it's sealing, and the standing valve stays closed. So you are basically helping move the fluid that already got into the barrel move higher. And this process brings fluid slowly to the surface. Beam pumps are driven by prime movers, can be motors or engines, through a gearbox with an attached crank mechanism at adjustable pumping speeds. The back and forth motion of the working beam transmits up and down motion to the downhole components through linked steel cycle rods. Through this motion, the cycle rods activate the downhole pump, which operates through the dynamic status of two valves, the standing valve and the traveling valve. In every stroke, a volume of produced fluid is lifted through the cycle rod's tubing annulus and discharged to the surface. And now that since we are in the office, in my office, we are not in the upstairs in the room, let me show you something. This little beam pump that is basically moving up and down. It shows you the little part. I mean, from the camera, it's hard to see, but it's beautiful, wooden piece. It needs some fixing, but yeah, I mean, it basically it operates. This is like a little cloth string, and you have this thing moving up and down, which indicates basically that's the wellhead, let's say. And obviously there is no downhole pump associated with it. Need to fix it at some point. Oops. Actually, my former girlfriend bought it for me after I passed my dissertation defense 6 years ago or something. Anyway, so now downhole is a different story. You have the downhole pump, which I said is like a bicycle air pump. And this one I want to show you. So let's do this. it might be hard to understand how it works, but I think this video helps if you can, oops, traveling valve closed, traveling valve open, now standing valve closed, and then upstroke, standing valve open. So downstroke, fluid gets higher. Upstroke, the fluid moves into the barrel. So that's how the system works. If you are wondering how, if you sit down and stare at this video for like 1 minute and a half or something, you will understand eventually how it works. Like, is the dynamic status of the two valves not change? Okay, now remember what I said. Pump jack is a bad idea. Beam lift is also a bad idea. And you were wondering why. I know that these are colloquial names, of course. And I use it myself when I'm in the field. But this is because there is other ways you can achieve the same thing with the same method, the same system. It's less common, but look at this on the right. It's basically a long stroke Sakya rod lift. So it's basically longer stroke options. And they are made, I think, by Weatherford. Weatherford makes most of them. We passed from a few of them in on the way to Williston last week and back. And I asked the students if they knew what was that, and nobody knew. But it's basically the same thing. It's just a longer stroke, more or bigger barrel, etc., etc., downhole barrel, etc., etc. So more fluid coming out on the surface. Now it really works the same way. It's like a conveyor belt, and it's basically moving the not the Sakharov, what's the name? I forgot. Just like we have here this one, is the brindle, the part of the Sakharov that you see on the surface, and then you enter into a polished box, and then polished rod. Sorry, polished rod is basically the top part of the Sakharov. Now, polished rod goes in and out of the surface. You see a little bit on the surface, and then you don't. So it goes in, downhole, and up. And after that, you have Sakya rods. But the point where the polished rod goes in and out of the hole is called the stuffing box. And that's where you can often have leakages. You want to suppress leakages in the stuffing box, and you need to replace it every now and then for that reason. Now, with the long stroke pumping units, you have a polished rod, it's longer. You have a load belt that moves up and down at a much bigger sort of oscillation amplitude than the beam, the Sakya rod pumps, the pump jacks. You have the prime mover at the back, which is basically a motor, and the counterweight right there. It's sort of like the thing that you do at the gym. You have the counterweight, and then it moves up and down accordingly. In this case, you are moving it with the gearbox and the prime mover, and basically it works the same way as the pump jack, especially when it comes to downhole. It has some better capabilities, so longer capabilities. It's like for a well that is capable of producing a lot. Beam lift monitoring using a dynamometer. Now, how do I identify problems with a beam lift? And there is people who are working their whole careers is dedicated on beam lift optimization. So I will use something called a dynamometer. Variations of the stress load against displacement experienced by polished rod over each stroke are recorded by a special instrument called the dynamometer. So we said we have the brindle, which is always on the surface. Then we have the polished rod that moves in and out of the stuffing box. Everything below the stuffing box we don't see. Everything above the stuffing box we see. And then we have a series of cycle rods until we make it downhole to the downhole pump. Now, there is a very long string of cycle rods, and actually, if you see some, try to see, you'll see that you can twist it even with your hands. They are very, very easy to break. Very, very easy to break. Extremely easy to buckle. Extremely easy to buckle. I bet if you step on them and try to push it, you can actually destroy one. I mean, it's quite a delicate piece of equipment for using it in a well. So what we do, it basically goes downstroke and then upstroke. In the upstroke, it weighs very heavily. So what happens is that the whole string extends. So if it extends, it becomes taller. It has a certain Young modulus. What happens in its width is that it's becoming narrower, slimmer. So what you do is that you put a strain gauge right there at the polished rod and maybe have a strain gauge downhole and see how the width of the width of the polished rod and downhole changes with time. So there was a student trying to come in, but I was like, I have class. They think I'm upstairs. But anyway, a dynamometer is an optional piece of equipment. It's not in every rig. And basically, using it wisely, using the readings from it wisely, it can tell you how many it's like what problems you may be dealing with and what works abnormally. An experienced person is gonna read the what do we call the dynamometer card or dyna card and tell us what is wrong. The shape of the survey recorded by the dynamometer is described on the dynagraph or pump dynamometer card and can reveal problems affecting the equipment. Now, before getting on what shape says what problem, let's just first see how a good one should look like. A good dynagraph should look like. And it's on downhole, it will be rectangular. Why rectangular? Because it doesn't change length downhole. The change in length gets bigger and bigger as you go to the surface, and it's maximized on the surface. On the polished rod, it's a parallelogram. Okay, and any wavy lines have to do with friction losses. So we are rectangular at the standing valve, and then at the traveling valve and upwards, we are gonna go parallelogram. Now, if we are comparing traveling valve and surface, they are both gonna be parallelogram, but it's gonna be much more pronounced parallelogram on the surface. On the surface is where you see the biggest displacement, actually. Now, what this thing is that you put on the polish rod and downhole is basically what we call a strain gauge. It measures how slimmer the tube is becoming, and from that, it infers how tolerant it becomes. Dynamic effects due to friction make the dynagraph shapes wavy. It's a major diagnostic tool for the beam lift. And this picture shows more details on the beam lift. It's sort of like that toy I showed you. We have the pitman that is moving with the cranks and the counterweight. Everything is being rotated by the prime mover through the gearbox. Stuffing box, T, casing head, casing string, cycle rod, rod pump, and so on and so forth. Polish rod, center of saddle, bearing, etc., etc. Some of them are details. You don't really need them. rod pump, they really mean the downhole pump, actually. Now, this is different shapes that you can get for the dynagraph. And every shape means something, like insufficient liquid supply or gas influence. They look very similar. It requires a very trained eye, somebody with experience, who learned under somebody by working with somebody with experience to read those dynagraph plots. It's a it's an invaluable, if I may say, diagnostic tool, an invaluable diagnostic tool. And if you want to become good at it, I mean, you really need to spend time going from one place to the other, looking at different pump dynamometer cards and what they register. A common problem that comes with depletion, though, is what we have. What we call fluid pound. That is, the pump is not getting filled entirely with fluid. And in this case, this is bad. It means I'm under operating my artificial lift system. I don't let the barrel downhole fill up. So this is very well related with artificial lift pumping speed. A common problem triggered by reservoir depletion, so it will happen regardless, where the downhole pump does not get sufficiently filled with fluids, and simple remedy provided by Bomer and Podio. Reducing the pumping speed can often solve fluid pound in issues. It basically lets the barrel fill up. Reducing the pumping speed, yep. Not many practitioners on the field are aware of this, especially the ones that are trying to advocate that you pump with as high rate as possible. Speed kills not only on the road is what Dr. Bommer used to tell us. And this is an example that I drew with data he gave me, actually. I wrote that article in the way I had, and before we published it, I was already a postdoc at CSM, but I told him, please review it, make sure that everything is fine. And then he suggested I build a plot using, he sent me the data. So this dynagraph is not at the traveling valve. It's at the downhole pump, probably the standing valve, the red one, and then at the polished rod on the surface. So the normal one is what you see with the, well, with the red is the normal one on the part A. Red is correct. And then on the surface, you have a problem. You get blue instead of green. And it looks like it might be okay, but the problem is that it's basically non-idea. So as a result, eventually, this is fine. Part A is fine. Part B is not fine. It became very similar to the blue became very similar to the shape we see up in a different in this slide, and the like gas influence or insufficient supply and friction. These are the fluid pound stuff. Oops, where is it? Now, at A, I'm okay. At B, I have a problem. Okay, I have clear fluid pound issues. The barrel is not letting enough fluid to keep the everything else constant. So the solution to that is that we just reduce speed. We have it down from 10 SPM to 5, which is pretty slow. It's pretty slow. It's one cycle every 12 minutes, which 12 minutes is a long time. You probably don't see the pump jack moving. You need to sit down and look at it for a long time to understand that it's moving. But as a result, the problem of not filling the pump now is no longer a problem. And we fill the well, the pump, maximizing production from it as much as we could. Just by slowing the pumping down, I mean, we were able to help ourselves with that. Now, another method, if there was audience, I would have asked if you guys have any questions on CBHP, but I think it's okay. So let's move on with the electric submersible pump. And this was a more delicate sort of piece of equipment. It was invented by a Russian person, Russian-born person that moved to America later in his life. It's an electric motor with the proportions of a slim fence post, which stands on its head at the bottom of the well and kicks oil to the surface with its feet. That's what Tulsa World newspaper used for describing the 1500 feet, sorry, the 1500 feet, the electric submersible pump. Now, in 1911, it was Mr. Armais Harudunov who invented the first electric motor capable of operating underwater. And then it basically led to operating under kicks and gas, and then basically making a big name for himself. And actually, it's very used a lot today, actually. Used a lot today. Due to its small surface footprint, smaller than the pump jacks and certainly smaller than the long stroke pumping units, ESPs are considered environmentally friendlier than other AL methods, such as sucker rod lift. How do ESP works? ESP has a series of impeller diffuser sets. The impeller creates a fluid velocity, and the diffuser converts part of the induced kinematic energy or kinetic energy into pressure. The higher the required discharge pressure is, the more impeller diffuser sets are needed. You are limited by the maximum amount that the pump can carry, of course, as you can imagine. The available power in an ESP can be used to generate either a higher discharge pressure or a higher flow rate. Thus, each pump size has natural limits on pump flow rate and discharge pressure. So there is so much you can do. And generally, if you increase one, you need to slow down the other. You cannot increase both at the same time if you are on capacity. Otherwise, you're going to break things. If you break things, you cannot really fix anything on ESP without bringing the workover in place, the workover rig. And workover rigs onshore are quite important. Imagine offshore how much expensive it's going to be. Now, offshore use of ESP, and that's a very widely misunderstood question. The first time I went to Petron Bowl in 2012, it wasn't to compete, but to see and understand if this is something I can potentially do. So we went to San Antonio for ATC 2012, and UT was the reigning champion team, and basically they got a bye the first round, and they were playing Wyoming University in the second round. And everything went down to one question, basically, and they asked what is the most common artificial lift method used offshore, and they said ESP. And ESP is a good answer, it's not a bad answer. However, it's not a truthful answer. The offshore ESP that is more popular, that is used is most popular, is basically something that we're going to learn later called gas lift. And there is reasons for that. There is reasons why ESP is not popular offshore, and that is because they need a lot of fixing, and that takes money. Imagine having to bring a workover rig offshore just to pull out your well. Now, California found a way to mitigate this situation in true Hollywood fashion. If you are in Long Beach and you look into the sea, into the ocean, you're gonna see some islands that look like resort islands, and they are basically what they call thumbs islands: Texaco, Humboldt, Union, Mobile, and Shell. Those five companies grouped together and made like a consortium of islands, those four islands, which they built in the late 1960s at $8 million. Today, I doubt 8 million can get you a pipeline from here to my apartment, honestly. Now, those islands are very decorated, and they produce oil from the Wilmington field, which is very famous Long Beach field that in the 20s they had rigs next to each other, and basically they said you can jump from one derrick to the next. Now this is how it looks like in real life. I took this picture because I was there a few days before COVID 2020. So the way the rig is configured, you're gonna see later in the next slide, is basically like a NASCAR track. You have the oval, and you have the oval, the rig moves around, and you have wellheads, thousands of wellheads inside that oval. And on the surface of the island, which is basically a highly decorated production platform, you have a lot of facilities. And those facilities you rarely see in an offshore production, in a real production platform. Some of the things that you see there in those islands is workover rigs that are there full time. And also all the wellheads on the surface, you can see them, like you can access them. This makes it look more onshore, an onshore project than an offshore one, which bears a lot of benefits. And some other not so benefits, not very good benefits is, for instance, everybody's watching you. If you make a mistake, it's like you're operating in a fish tank. Everyone can see you. But the workover rig, having a workover rig, which I don't see in this picture. Oh, I do see in this picture. What am I saying? This one. It was in front of me. Having a workover rig there, I mean, can basically work 24 hours a day, and there is over 1,000 wellheads. I bet you some of them need it anytime. So you can do the work. I guess some people are disappointed to find out that what these islands are for. When I was young, no, sorry, what am I saying? Those islands are they are named after the Apollo astronauts who lost their lives during the Apollo program. The three that were in the capsule of Apollo 1 that burned alive. What a terrible death, by the way. They were doing testing inside the capsule. The capsule was pressurized with pure oxygen. I think they said somebody had a brush, a metallic brush in his pocket or something. Somehow a spark went on, and basically it ignited the whole capsule, and the hatch was opening from outside inside. So because the pressure inside was very high, they couldn't open the hatch. So by the time they were able to open it 1.5 hours later, the poor guys have burned. And there is another guy who lost his life. I don't know in what mission necessarily, but the names are Chaffee, White, Freeman, and I forget the other one. The one I went to was White, the white one. Grissom, of course. So Ed White, something Grissom, and so on and so forth. Now look at, come on, Texaco, Humboldt, Unocal. which is Union Oil of California, Mobil, and Shell. This is us. This is the working rig. It's very useful to have a working rig offshore. And look at the wellheads, one next to each other. You can really jump from a wellhead to the next. Now, what are those rigs, those platforms doing mostly? It's a story because this field was produced very fast and hard during the 1920s. The area in Long Beach is very, very clear if you stand in certain areas that the area has subsided from the production from that particular reservoir. So what those right now they are not owned by, they are called the Thumbs Islands, but they are not owned by the Thumbs companies. They are owned by California Resources Corporation, which used to be Occidental, that span off these four islands. The company that was running those four islands, the operator, they spun it off and they call it California Resources Corporation. What they do is that every platform has about 1,000 wells in each, right? So they buy water from the city, the wastewater from the city, and as it is, they inject it. As it is, they inject it. They don't need to treat it, they just inject. They inject it, and what happens is that basically they are mandated by law, by the regulations, that they inject 5% more than what they produce. So they inject at very, very, very high water oil ratios, very, very high water cut, as we call it in the field. And they are producing very little oil. And as much they produce oil is better, is good. The more oil they can produce, the better. But they're mandated by the state laws that they have to inject more than 5% more than what they produce. So ultimately, the goal is to find that subsides as much as they can. Now, other than the Thumbs Islands, you can still see it offshore. Not a lot of places, though, because of the maintenance cost. Like the maintenance cost, imagine having to pull over the pump, the ESP, in an offshore site. I mean, it's gonna be, it's gonna provide, it's gonna provide, it's gonna be like an $8 million operation to fix that ESP, because you need to pull it from downhole, see what is wrong, and fix it. You cannot fix it from the surface. So it's not very popular, as you can imagine. Now, a lot of moving parts imply a lot of maintenance reasons, as you know. The Thumbs Islands have workovers, snapping rigs permanently on location. They have semi-trucks permanently on location. So they can do a lot of stuff that you can do onshore there, even though it's not real or offshore. It's like pseudo offshore. Now, another method is the progressive cavity pump. Progressive cavity pump. That one we borrowed the concept from aerospace or aviation. It involves the use of a downhole positive displacement pump, which evolved from a helical gear pump concept developed by René Moineau, who was an aviator. Basically, you are trying to combine sucker rod with ESP, take most of the advantages of both, and eliminate as much of the disadvantages as you can. It features low capital and running cost, strong reliability, and a small surface footprint. PCPs are becoming an increasingly popular artificial lift solution. So they are becoming more and more popular as time goes by. So how does it work? You have a stator that the rotor is rotating inside it. The stator is, sorry, the bigger part of the stator is made of something called elastomer, which is very easy to replace if something goes wrong. But again, it's downhole stuff. And then on the surface, you just see the electric motor. That's it. The helical chromium coated steel rotor and the elastomer molded stator are aligned eccentrically at the bottom of the production tubing, creating fixed size pump cavities. So as this is rotating, you have a gobble of oil here. No. Let's make it orange, thicker pencil. Gobble here, and then the rotor is rotating inside the stator. The gobble finds itself here, then here, then here, and then here, and then it goes up like that. Now the stator, the rotor is touching the stator. So both of them are wearing each other down. As the rotor turns inside the stator, the rotating motion makes the pump cavities open and close, carrying fluids up through the wellbore in an orbital manner. A prime mover on the surface provides the motion, which is transmitted to the rotor through the wellhead using a cycle rod string. Now, how do PCPs work actually? For highly deviated wells, often using a downhole motor, eliminating the need for a cycle rod string. However, in this application, ESP may be a better choice if you have a highly deviated well, because you don't have anything making its way to the surface. Yeah, ESP is better for inclined, highly deviated wellbores. The elastomer stator can be a limiting factor on the pump depth or the discharge pressure, because as discharge pressure increases, pump efficiency decreases. The rotating cycle rods can cause significant wear with the tubing should they come into contact, and they will come into contact. It will heat up, the elastomer will start melting, and then at that point you start either leaking or you need a new pump downhole. Now, gas lift is the last method that we're going to talk about of artificial lift, and I left it at the end for a reason. One is what we talked last time is basically, how do you say, traditional artificial lift methods. Now, that affect basically the fluid, they give more energy to the fluid inside the wellbore to make it move. Gas lift affects the oil inside the wellbore per se. It lowers its density. And as a result, it helps it move up. So many people, because you are changing something in the oil that you have on the surface, they call this reservoir stimulation method. So be aware, gas lift is also considered a reservoir stimulation method. The aim of it is to inject gas inside the wellbore at certain points, have it mixed with the oil inside the wellbore and make it more gaseous, decrease its density, and help it move up. The injection gas can be supplied from nearby wells and gathered using a compressor. Conventional gas lift valves are mounted into mandrels on the production tubing, while wireline retrievable gas lift valves are set onto the side pocket mandrels. It's often considered a stimulation method, and I think this picture would make you understand what I'm trying to say. You have those conventional gas lift valves on the surface, on the side of the tubing, sorry, production casing or production tubing. Those, when the pressure goes up in the annulus, we have red fluid, which is gas. If the pressure of the gas goes up, as we see at bottom, they have this little piston that moves up and allows fluid to enter the inside of the tubing. As the red fluid enters the inside of the tubing, it makes the fluid inside the tubing from green go to red, go to lighter green. That means its density is lowering down, and you can basically move the fluid up in the surface. Now, this is often considered active stimulation method because you change the type of oil present, and obviously it will have to be cleaned up and then maybe circulated back down hole or sold to the nearby pipeline, if there is nearby pipeline, or just flared. Gas lift can be employed over a wide range of well conditions, as it can cope well with abrasive environments and sun production with low workover cost, especially popular offshore, along with onshore locations where gas source is available. It could be gas coming from the same well. For intermittent gas lift operations, as we call it, an intermittent, something that stops injection and then starts it again, installed on the surface, controls the gas injection timing using fluid-operated valves, which open and close when the tubing pressure rises or falls. I tried to do something like that, but I wasn't able to when I was going to Houston last time, or on last October. I go to Houston very often, actually. I joke with my graduate students. It's not a joke, it's true. All my exes live in Texas, just like the George Strait song. But I generally go for conferences, of course. It's not to see anybody. But I do have a good time seeing old classmates. And last time, especially for HFTC on February, I saw a classmate that I was very close to, Vietnamese classmate. I hadn't seen him for 8 years, and we were like siblings at school. We did undergrad together and masters together. Then he graduated. I left and went to Louisiana, and I hadn't seen him for 8 years, believe it or not, which is ridiculous. He took me to his home, showed me his pool, told me some stuff about how they go in the industry. It was a little bit depressing, but yeah, I mean, I wasn't able to meet his kids and stuff. Maybe this time, if we meet, I guess. But I did enjoy it. So keep in touch with your classmates. There are some things that you can't really discuss with the lower generation of workers or the higher generation of workers. With your classmates is like sibling relationship, you know. Anyway, for intermittent gas lift operation, we use something called intermittent, which stops injection and then starts it again. And what determines how it gets activated sometimes is a pressure threshold. If they go above a certain pressure, they let fluid go in. If they go lower than a certain pressure, they let fluid go out, or it really depends. It really depends. Or the opposite, actually. If the pressure drops below a certain level, they open, they allow you to inject. If it goes above a certain level, it stops you from injecting. You need to bleed off the existing pressure and then see how to move on. Alternatively, throttling pressure valves are used, which open and close in response to casing pressure increase or decrease, respectively. Now, these intermediate and throttling pressure valves, some of them can be made active. So you change the pressure and therefore they activate, or make them work passively. I prefer if they work passively because they need less human interference. So you can have them open or close respectively from things that you do on the surface or things that you plant from the surface. Now, we talked about 4 methods of artificial lift, but we haven't talked about the elephant in the room is how do we select which one to use? The old saying in the field was you go from ESP to pump jack to plug and abandonment to P&A. And that is you go from a mature reservoir that cannot deliver, depleted reservoir, to a very depleted reservoir that cannot deliver, to basically a reservoir or a well that nobody wants, basically. And you have to, a well that costs you more to operate than what it's giving you. So you might as well close it, plug and abandon it. But the method, the procedure that you are gonna use, the process for selecting which artificial method fits your well the best is a topic that has been going on from the early to late 80s. Several factors are considered when selecting the best artificial lift method for a particular well. The artificial lift selection process presents discussion of the available artificial lift methods, in addition to the strengths and weaknesses of each method in relation to the existing well installation and reservoir. So it's the combo between reservoir and well, VLP and IPR curve, that dictate what artificial lift method or system you can use. Despite artificial lift selection being a multifaceted problem with unique challenges for each well, expert programs, as they called it, have been developed since the late 80s in an effort to standardize and computerize artificial lift method selection. And these are the criteria that they are looking for. We have what areas each type works best, and then we see our own scenario and we try to fit it where it makes the most sense. For instance, Saker rod lift is robust, flow rate flexible, applicable to a wide range of flowing bottom hole pressures, can tolerate moderate sun production, not a lot of sun because it will start abrading. It can handle high oil gas oil ratios, not demanding a sound wellbore. The weaknesses are they cannot handle foams, difficult with very high GORs, deviated wells is a problem because of the Saker rod string that has to bend as well, can be very expensive, multiple moving parts. What about ESP? ESPs are capable of lifting high volumes. They are good with deviated wells with small footprint, environmental footprint, or ecological footprint. It's unfriendly to solids, very unfriendly to solids, even salt particles, especially. Unfriendly to viscous oils and paraffin, which it's okay to use in the Saker rod lift. Expensive and costly maintenance. PCP has a small footprint, applicable to a wide range of flow rates, can tolerate high GORs, can handle sand and so on, can handle sand at low rotation speed, can handle viscous oils, cheaper than Saker rod lift, actually, yeah. You don't need the big pump jack. Possible to run as an electric submersible, and then you basically have ESP without ESP, but a PCP downhole. They are limited by flowing bottom hole pressure, high rod rotation wear because of the that touching between the rotor and the stator can cause a lot of problems. Not applicable to divided wells with rods, less robust than sucker rod lift, cannot handle foams, cannot handle high GORs. Now, gas lift is good for divided wells, small footprint, applicable to a wide range of flow rates, can handle some production, which is unique, can handle foams, no moving parts, and relatively inexpensive and simple. And then the drawbacks is that it requires high pressure gas supply, facilities revamp, compression requirements, sound casing requirements, not possible at very low FBHPs, and difficult with viscous oils and paraffins. AL selection process and well screening criteria. A sophisticated quantitative version of table like the one on the previous slide is at the heart of any AL selection process. Any computer program, if you use the most modern version with artificial intelligence and or a surrogate model, or you go back to the 80s and see what they were doing, and they were doing some excellent work back in the 80s. They all have a table. They are all operating based on a table like the one I described in that slide. Now, that table is mine and came from that article I wrote. And it was written with the help of Dr. Bowman, who has enormous experience in this kind of stuff. Now, this is not comprehensive. This is not comprehensive. And then I missed. But you can improve it over time. But ultimately, this is what you need. You try to have a table, and then you fit your scenario where you think it belongs. These programs incorporate workflows which consider user inputs for a well and its operating conditions to determine the most appropriate artificial lift method. Now, modern data analysis techniques, and I know some of you in class are very interested in those stuff, or they were interested back when it was fashionable. They are very popular avenue for further streamlining the artificial lift selection practices. So, for instance, if you want to do something in the data analytics spectrum, probably artificial lift selection practices is a good candidate. If you do it well, it will give you good results. It will give you a good application and good utility of your product. With several workflows following economically guided techniques. So money also matters. Money also matters. Maintenance costs. Pumping fast also brings other problems. Remember, pump slow. Speed kills, not just on the road. Now, and that was module 5. Summary. We learned what is artificial lift. We learned what are the goals and purpose of artificial lift. We talked about the relationship to well performance that we saw in module 4 and field management. We talked about artificial lift performance monitoring, and we overviewed 4 common artificial lift methods. And then finally, we talked about artificial lift selection process and well screening criteria. And this is the end of the material for this class. I won't see you on Tuesday, but I will see you on Thursday, where we're going to talk about the final. On Thursday is also the deadline for the term paper. So if you are starting right now, it's already too late. But if you start and you spend a lot of time, you may be able to make it. But yeah, I mean, you have to have read a lot of papers. And I don't think you can read a lot of papers from now until next Thursday in 1 week. That being said, I don't think that anyone started this late, but if you left it until now, you probably made a mistake. But yeah, I mean, feel free to shoot me an email with any questions or the TA. The TA will be in town all throughout. I won't be able to answer emails very fast, very swiftly when I'm not home, but at some point I will be going back to the hotel and I will be reviewing my emails. I also have some deadlines myself in that day. That day I'm presenting sometime in the afternoon, and I have like a bunch of deadlines, like 2 deadlines or something myself. So it's a crazy life, even after you are done from being a student. This year in particular has been quite a torture. It's worse than last year, and last year was already hard. Um, but yeah, I graduated already 2 students. That means I'm down to 2. So I guess my workload is gonna go a little bit down in the future. But I still have your excellent TA to graduate and another person, another student as well. And maybe I get some more on the process. So that was module 5. If you have any questions, let me know. The final exam will be comprehensive, all 5 modules, and we are going to talk about it next Thursday, but it might be smart to start revising before then, because next Thursday is 7th, and the exam is on the 12th. You may want to start revising early. It's a lot of slides, a lot of material. And with that, thank you very much. Have a good evening. And yeah, I will see you next week, next Thursday.